Now, okay, for the reaction today is nitration of methyl benzoate. Methyl benzoate is an aromatic compound. So this reaction basically is a reaction of aromatic compounds. The type of reaction is a substitution reaction. What's happening in this reaction, a nitronium ion, which is a NO2 plus, is going to replace a hydrogen from the benzene ring. Benzene ring is known as an aromatic compound and is very stable. And what makes the benzene ring to be stable? It's the delocalization of pi bonds inside the ring, which can generate greater number of resonances, or at least resonances, and then the resonances is going to make the molecule stable. So if you have pi bond, which you learned in chapter 8 of organic 1, you can add nucleophile or electrophile. You can break the pi bond and saturate the double bond, change it to single bond. Bromination of alkene is a very fast test. Bromine is a brown color. When you add to a compound that has double bond or triple bond, the color disappears. That means that it reacted quickly with the alkene or double bond or triple bond. The type of reactions shown for bromination of this alkene is called addition reaction. In comparison, for a benzene ring, there is no addition reaction. That means in addition reaction, pi bond breaks, 2 new sigma bond forms. When it comes to benzene ring, because you have 3 pi bonds, you would expect that one of these pi bond breaks and a bromine would be added to each carbon. But that doesn't happen, and the reason it doesn't happen is because benzene ring is aromatic, and aromatic translates to stability. And when you have a compound that is aromatic, doesn't want to lose that aromatic property or aromaticity, meaning doesn't want to lose stability, so the pi bond stay. So we don't have addition reaction here. Instead, we do have substitution reaction. Each of these carbons in the benzene ring, they carry 1 hydrogen. So when you take a bromine and replace the hydrogen, basically add to this carbon, you see there is no bond breaking of the pi bond breaking, so it's not addition reaction, but it's replacing a hydrogen, so that's why it's known as substitution reaction. So we have a substitution reaction here is taking place. This bromine can replace any of these carbons. It can replace the carbon 1, 2, 3, because there is no group attached to benzene ring. So bromine can take any of these hydrogens and replace it, and the name still is going to be bromobenzene. In order to do bromination of a pi bond from alkene, you don't need a catalyst. In this case, for aromatic, even though addition doesn't take place, is a substitution reaction, but still you need a very strong catalyst to change your electrophile to a very strong electrophile, so it's brave enough to attack the benzene ring, because benzene ring is very stable compound. So if you want to make it react, something to react with it, it has to be, or better be, strong. The electrophile is going to be strong, like a Br plus, and you will learn that in lecture. Br plus, the Br with the 2 electron is going to be added to Fe, because FeBr3 is a Lewis acid, and Lewis acid, of course, because it's missing electron, it counts as Lewis acid, is looking for pair of electrons, so it takes that pair of electron with the bromine from the Br2, so the other Br would have positive charge and acts as electrophile, is looking for electrons, and it comes and replaces a hydrogen. So it doesn't matter which location. When it comes to a benzene ring that you already have a branch on it, like in this case, that branch is called a carboxylate. Okay, is a CO double bond, CO single bond. It could be like a methyl group. So this is like an ester functional group, but this functional group is called like a carboxylate. So the that is attached to the benzene ring. When you have one group attached to benzene ring, then these carbons on the benzene ring, they are not identical all throughout. I mean, all 6 of them are not identical. There's one that is carbon 1 that carries the functional group. The carbons adjacent to that, or position 2, because if this is a carbon 1, next to it is going to be carbon 2, and if you count it down, next to it, then the down part is going to be carbon 2. So carbon 2 has a name also that is known as ortho. Then carbon 3 with respect to the functional group is called meta. Carbon 4 is called para. Now, if you didn't have any group attached to benzene ring, this bromine can sit in any of these carbon and replace any of the hydrogens. When it comes to a carbon that already has substitutions, it depends on the nature of the branch that is already on the benzene ring. The incoming group can go to either ortho position or and para position, or it can go to meta position. So it's selective now. It's not like general, or it's not all identical, it's not symmetrical. So it's going to be determined by the group that is already on the benzene ring. So this group already on the benzene ring is known as a directing group. It's going to direct and say you can go to the ortho position or go to meta position. So you get like a major product and you get minor product. So it depends on this group. If this group is electron withdrawing group, how do we know the group is electron withdrawing group? Because it's going to have the element attached to the benzene ring is going to be electron deficient. You have a carbon here, 2 oxygens are pulling electrons away from that carbon. So that carbon feels positively charged. So if the carbon is positively charged, it's going to pull electron from the benzene ring. If the group is electron withdrawing group, is going to withdraw electrons significantly more from ortho and para position, but leaves the meta position alone. Okay, so it's going to deactivate. The other name for electron withdrawing group is called deactivating group. Deactivating group is going to pull electron from ortho position and para position. So the meta position is not deactivated. Now, it's very, so when the nitro group comes in, the nitro group in this reaction, because this is the chemical reaction that is taking place here. A nitro group is coming and replacing hydrogen, is going to replace one hydrogen. Our job today for this experiment is to find out what would be the product. Based on physical property of the product, we are going to find out, is it going to be meta, is going to be ortho or para product. And then we have to be able to, we should be able to explain, we already know that is a meta product because this reaction is given here, but we have to explain and discuss why this is a meta product. Why did it go to the meta position or carbon number 3 with respect to this carbon 1, which carries the functional group? This is ortho and that is a meta. So we could have ortho substitutions, which is this one. If it goes to carbon 2, it goes to carbon 3, is going to be meta substitutions. If it goes to carbon 4, it's called para product. So we could have a para product, meta product, or ortho product. These terms, you have learned these terms already in chapter 12 or experiment 12 as like 2-chloro, 3-chloro, and 4-chloro. So if it's a 2-chloro, the other name would be orthochloro. 3-chloro, just like metachloro, and 4-chloro would be parachloro. In this case, is a nitro, so it could be metanitro or it's going to be orthoparanitro. The answer to that question or the explanation why this is a meta, because the group that we have on the benzene ring as the ester group, it's a electron withdrawing group, and we already talked about electron withdrawing group. Because this carbon that is directly attached to benzene ring, it feels positive charge. It carries a positive charge because oxygens are pulling electrons strongly. Okay, so it's electron withdrawing group. If it withdraws electrons, that's one fact that you need to identify. Is it electron withdrawing group or is it electron donor group? The other fact that you need to know in this experiment, you learn, and then you learn more about it also in lecture, that the positions that are ortho, meta, or para. What is ortho position, meta position, or para position? The third factor is like if this group is electron withdrawing group or deactivating group, that's another name for it, is going to deactivate or put positive charge on the ortho positions and para position. NO2 plus, this is your nitronium ion, which is going to act as your electrophile and is going to come to either ortho position, meta, or para. Why doesn't go to ortho position? NO2 plus is going to be generated in this reaction with this mechanism as the electrophile, and it has a negative charge. Okay, so should it go to meta position or ortho position, or why is not going to ortho para position? Can you answer me? Why doesn't go to ortho para position? Should it go to ortho para position or should it go to meta position?
I can still not.
Okay, I'm waiting for the response. Let me check the chat. Okay. Oh, NO2, the nitronium ion, which is the NO2, is going to go to either ortho, meta, or para. My question is, why does it go to meta and not to ortho para? Or can you tell me, is it going to meta or ortho para? Either way, you can explain better. Ahmed, you said meta position. Why meta? And Tyler, you said also meta position. Why does it go to meta and not ortho para? Cherise, you could answer it also, either one.
I would say that it's meta position because it is the electron withdrawing group on the deactivating portion of the benzene ring. So
okay. Can you also explain based on this diagram? Because this diagram kind of shows the mechanism for this reaction also. Can you explain based on this diagram why NO2 doesn't go to ortho or para position? Based on that diagram.
Which diagram? The chart or the mechanism? I'm sorry.
The highlighted one. What the part that is highlighted? Do you see the part that is highlighted? Does it show that?
No, I don't see which.
You don't see highlighted blue, but I highlight this part. It's not showing a blue highlight? No? Okay.
All I see is you.
Oh.
Yeah,
You have to
see you. I don't see.
screen.
Are we looking at table 14.1 in the book?
No. What do you mean? I was sharing.
It's not there. It's not showing. Yeah.
Seen it. There you go.
Is it?
Oh, okay.
Okay. Okay. This I was sharing the document, and when it stops sharing, please let me know so I can go back. I don't know why it stopped sharing. Did it never share?
We couldn't see anything. Never. It was just you.
Oh. Okay.
None of that. Yeah, we saw none of that.
And when I said this reaction, you should have just catched that either something went wrong and it didn't start sharing, because I said let me share the lab
reading the book as we were talking and trying to figure it out, but we couldn't see it.
That's okay. That's okay. It would have helped to see these reactions so you understand better. So in this reaction, when you have your aromatic compound, the aromatic is the benzene ring you have here attached to a carboxyl group that gives you ester functional group. And with the ester functional group, you would ester functional group is a deactivating group. Okay, why is deactivating group? Because is the carbon has attached to oxygen. Oxygen is pulling electron from the carbon, so it makes the carbon positively charged. And if carbon feels electron deficient or positive, it's going to pull electrons from the benzene ring. So it's known as the deactivating group or electron withdrawing group. This part of the reaction, when you have the reactant that you are writing over the arrow sign, is basically the reagent that you are using. The reagent here is nitric acid and sulfuric acid. Nitric acid plus sulfuric acid generates nitronium ion, which is the NO2 plus. NO2 plus by nature is called electrophile. And why is electrophile? Because it carries a positive charge, right? So it is electrophile. So NO2 plus is generated from this mixture, and it is electrophile because NO2 plus has a plus charge, so it's looking for electron. So when it comes to this ring, it can replace one of these hydrogens. So when I was explaining about this reaction, alkene, CC double bond with Br2, is basically test for unsaturation. Br2, it can saturate this double bond, it changes to single bond. This type of reaction is called addition reaction. But benzene ring never goes through addition reaction under normal condition because benzene is aromatic, is stable, doesn't want to lose its aromatic property. And since it doesn't want to lose its aromatic property, it doesn't want to lose the pi bond. So in addition reaction, pi bond is broken. Sigma bonds are formed, but what happens here is called substitution reaction. So if it's a substitution reaction, meaning that bromine is going to replace one of these hydrogens from the benzene ring, and if benzene ring has no other group on it already, all of these hydrogens are identical, so any of them can be replaced with bromine, and you get bromobenzene. And the catalyst is now, if there is a group already on the benzene ring, which is this group here, carboxylate ion, or carboxyl group for ester, and this group is electron withdrawing group. Can you tell me why is this electron withdrawing group? Why this group is electron withdrawing group?
The positive charge?
The positive charge on carbon, yes. Positive charge on carbon, and what is carbon that is directly attached to the benzene ring is electron deficient. That means it doesn't have enough electron. And the reason it doesn't have enough electron, because electrons from carbons are pulled out or pulled away by the two oxygens that is attached to that. So it's electron withdrawing group. The other name for electron withdrawing group is also known as meta-director in this type of reaction, meaning reaction, electrophilic substitution reaction of aromatic compound. So you get the other group, the incoming group, into the meta position. So they are called also meta-director. The diagram here, it shows that the incoming group, the NO2, it can go to ortho position, it can go to meta or para position. So you could have ortho, meta, or para. But since this group is electron withdrawing group, the major product is going to be meta product. That explanation is covered in the mechanism for this reaction. This is the overall mechanism. It doesn't give the step-by-step, but it's the overall mechanism. What's happening here is that since your group attached to benzene ring is electron withdrawing group, and you're also using sulfuric acid, you are going to protonate it, it even makes it more positive, it's going to pull electrons away from benzene ring. So first, you identify the group attached to it. Second, you identify the carbons as ortho, meta, or para. Third, you look at the charge distribution, saying that if you have an electron withdrawing group, it's going to withdraw electron from ortho position or para position more significantly, and it's going to leave the meta position alone. So going back to my question that I asked before sharing the document, I said, why NO2 or nitronium ion is going to meta position rather than ortho or para? I had a couple responses already, and they were correct. And if you can tell me again, or anyone else want to try it, why it doesn't go to ortho or para position. This diagram, it shows the mechanism. Basically, it shows the charge distribution. The charges on the ortho positions are positive, right? And para position, also positive. Your nitronium ion is positively charged. There's another electrophilic, is looking for electrons. And because of the repulsion between the positive charges, it's not going to go to ortho, it's not going to go to para, but it's easier for this group to come into the meta position. Okay, because meta position, at least there is no positive charge. And if there is no positive charge, it's going to be better than if there's a positive charge there. There is no charge. If it was a negative charge, it would have been perfect. But positive charge is the worst thing for NO2 plus to go close to, because of the same charges repel each other. But the meta position, because it's left alone, there's no positive charge, is a better option for NO2 to go and replace the hydrogen from meta position. Okay, now tell me if you have any questions about what we talked about, the theory of this reaction or theory for this experiment. Yes, Therese. Therese or Victor?
Yeah, I was.
Yes.
Yes, I was just curious. I'm trying to understand the difference between identifying meta, ortho, and para on the benzyl ring. I'm looking at on 36. It gives us. I just don't know how to really identify what is meta or ortho and para. So maybe that's what's hard.
First thing, good question. First thing, do you see where the blue color on the carbon?
Yes.
Okay, that carbon is called carbon 1. Okay, that is a carbon 1 because it carries the functional group here. So we named that, if you were naming, that was carbon 1. So if the other group, it goes to the carbon 2, that is ortho. So if it goes to this, like NO2 is on carbon 2, is ortho with respect to this. So it's in relationship, if it's a 1-2 position, is going to be, if the two branches are on the 1-2 is ortho. If they are on 1-3 is meta. So if the incoming group goes to this corner here, where it says M, then is a meta position. Okay, and if it goes to the P, then it would be para. So it's basically
so with respect. Yeah, it's with respect to where the functional group is attached, and then from then, so if it's on, so if it's on ortho, then you'll go to the next. It'll be either para or meta, or para, right?
Yes. So we are, the condition is we already have one. We have one group already on the benzene ring, and we are going to bring only one more. Okay, only one more branch. So let's say we are bringing just one NO2. And if we bring one NO2, it can go either to position 2, position 3, or position 4.
Oh, okay, got it.
If it goes to this side, top, then is again position 2, right? And if it goes here, in this case, it's going to be 3, here is 4. So the point is, if it's a 1-2, it's called ortho. with respect to two branches. One is already on the ring, the other one is incoming. So you see this one group here and the other group with these two, they are with respect to each other, they are in the 1 and 2 position, right?
Ortho.
Then it's called ortho.
Right.
And these two, so we have this one and this one, they are with respect to each other, they are on carbon number 1 and 3.
Okay.
And that's why it's called meta.
I got it.
This one is 1, and then the other one is on carbon number 4. So it's called okay. Ortho, meta, or para. So when you have three possible, yes, you have a 3 possible position for NO2 to attach, that means we have a major product or minor product and minor product. So we have to see which one is a major product, and that comes from the mechanism of the reaction. In the intermediate step, when the nucleophile is coming or electrophile is coming, this diagram here is showing that this is your intermediate, okay? That's your intermediate, and NO2 plus is coming in. Would NO2 plus prefer to go to ortho position, meta, or para position?
Meta.
Meta position, because?
Because there's no positive charge there.
There is no
all the other
charge there. Everything else, other positions, they have positive charge, except with meta. Can NO2 go here to this carbon up here? No, right? Because one carbon cannot have more than 4 bonds, so we cannot have addition of NO2 here. So the only choices are ortho, meta, or para position. And if you look at the mechanism of reaction, you see that the meta position doesn't have positive charge, and since NO2 is electrophile, it has to go where there is electrons, no positive charge. Doesn't like to go get close to the positive charge.
I have a question.
Yes.
So if that benzo ring were to be filled with additional, let's just say that the entire ring was filled with positive charges, what would happen to NO2 or any other reactant that we're using?
Okay, let me take one step back. When you bring an electron withdrawing group, it's going to pull electrons from the benzene ring.
Got it. Okay.
Fact 1. Fact 2 is going to pull electrons only from ortho position and para position.
Oh, I see. So there'll never be that situation won't really ever occur.
That's not going to be the case. Yes. So it's not going to pull electron from meta position. It is going to pull electron either from ortho position or para position. If it's electron donor group, it's going to give electron to ortho position and para position. So the effect of electron withdrawing is more significant on the ortho and para position. So it pulls electron from ortho or para, but it doesn't pull electron from meta. And that's something that you also learn more in detail in lecture. What we are going to do today, like if the aromatic was covered in lecture, which I'm sure is not covered in any lecture yet, you already knew all this. And you would come here and say, I already know that this is a electrophilic substitution reaction, and NO2 must go to meta position. So why I'm doing this experiment? The point of the purpose of the experiment today is to prove that if you have electron withdrawing group on the benzene ring, the incoming electrophile is going to go to meta position. And how are you going to prove that? Can anyone tell me, how would you prove that your product is going to be meta? Not say it in theory, in the lab, how would you prove it? How would you prove you have meta? Like, how did you prove what was your unknown for experiment 12? Similar, same idea. How would you prove that you have a meta product?
Like molecular properties?
And a specific property, if you can tell me, what's the specific property you are using today?
Melting point?
Melting point. And what are you looking for? What range of melting point you are looking to prove you have meta?
I see a 78 Celsius, but that's not a range.
Okay.
So.
No, that is actually the right number.
Okay.
The 78 Celsius melting point is for product. So for all of you who said that you are using melting point, you're correct. And if you said that the melting point of the product, if it's close to 78, then we know this compound is meta product, is not ortho product or para product. The information is not given for ortho and para, but you need to find those numbers from literature value or search for it. So you have other options, like if you had like a para product, it would be liquid at room temperature, or the melting point would be less than 25, or it would be very low number. Then you know that if your compound is solid at room temperature, is not that. If the other one has a melting point of, let's say, 100 or 110, then we know that's not the one. So if the melting point is close to 78, then you can prove you have meta product. Okay, let me look at the chat room to see if there's any questions I can answer. Okay, Karina. Okay. Any questions?
Sure. I still have the same question, and I wanted to ask you to apply.
No, I haven't answered your questions yet. Okay, I haven't answered your question yet, I think. So I will answer your question. So any questions about the theory for this experiment is electrophilic substitution reaction, and you could have ortho, meta, or para product. The purpose of the experiment is to make sure or to prove that your product is a meta product today. And the reason for that meta product is that the group that is already there is electron withdrawing group. Now we have a table here, and this table, it has electron donor group. These are the elements that they have pair of unshared electron, most likely, or they have a negative charge. And when you place them on the benzene ring, they act as electron donor group, and they activate like ortho-para positions, and they are known as ortho-para directors. Because if they give electrons to benzene ring, you get more electron in ortho-para positions, and when you bring electrophile, is going to grab that negative charge or electrons from the ortho and para position. Then you have groups that are known as electron withdrawing group. And if you have an electron withdrawing group, there's the other name for it is deactivating group, and the other name for them is a meta directing group. So these groups, these are basically the atom directly attached. So if you see this extension, that means that is going to be like carbon in this case is going to be attached to the benzene ring, or this carbon is going to be attached to benzene ring here. So we know that this carbon carries a positive charge because it's attached to 2 oxygen, or any of these, they are attached to another electron withdrawing group on the other side. So they are electron deficient. And if it's electron deficient, they are known as electron withdrawing group. And electron withdrawing groups are deactivating. At the same time, they're called meta directors. So the questions that you had on the in the pre-lab, the first question is basically saying, is this group activating group or is it deactivating group? Is it electron donor or is it electron withdrawing group? So you find that each of those functional group in this list, if it's up here as part of the electron donor group, then you would say, okay, it's going to be ortho-para director. And if you find it down here, it's going to be meta director. With one exception to halides, that halides, even though they are electronegative, high electronegative, and they are electron withdrawing group, but they are ortho-para director. Because when you attach any of these, you would see those pair of unshared electrons that you have on them. it would give electrons by conduction, and is going to it's the orthopara director. Now, how would you know what is orthopara, if it's activating or deactivating? Sometimes you have to memorize them, but what the way that I explain it, usually when I'm teaching lecture, I say, look at the element directly attached to the benzene ring. Does that element carries positive charge, or it carries like lots of electrons? Does it have pair of unshared electron on it directly? Then you can see, you know, if it's electron withdrawing or electron donor group, and then matching it is something that you have to memorize. If it's electron donor group, would be orthopara director, and if it's electron withdrawing, is going to be meta director. So let's look at this NCH32. So this is the amine and secondary amine. We're going to go to this table, secondary amine in R2. This is the secondary amine. The secondary amine up here is electron donor group, and if it's electron donor group, is going to be orthopara director. R is the generic name for alkyl group. So you have CH32, here it says R2. Like R could be any alkyl group. And that's how you kind of answer the questions. If I understand that it would be easier if the lecture had covered this part already, but we have some information in the ebook that you can use to answer these questions. So what is this group, COOH? Is this an orthopara or meta director?
Meta director.
Meta director. And why is it meta director? You can go back to table, or you can use my analogy that carbon is attached to two other oxygen, so it's going to be positively charged, and you find it also in this list as the electron withdrawing group. And because it's electron withdrawing group, it's going to be meta director. So from this. Okay. I think I did explain the theory for the reactions. Now it's your time to answer me some questions about the actual procedure and how we are performing this experiment. Let me just also look at the mechanism one more time. So this table, the set of reactions you have here, that's part of the mechanism because it's showing how your electron, your electrophile is formed, the NO2 plus, formation of NO2 plus. That is showing here that nitric acid is being protonated, and then H2O leaves, you end up with NO2 plus, and that is strong electrophile. That electrophile is going to attack the benzene ring in the meta position, preferably because meta position doesn't have positive charge. Ortho and para has positive charge, and where those positive charges coming from is because this group is electron withdrawing group. When it comes to the procedure for this experiment, you get 1 milliliter of the sulfuric acid, and you add 0.4 milliliter of methyl benzoate. You are using volume again, so make sure that you are, in order to get to the mass, you need to find the density for that. You multiply by density to get the mass. And then in another test tube, you're going to mix nitric acid and sulfuric acid. Nitric acid and sulfuric acid, then you mix it, that test tube is going to generate NO2 plus. Here it tells you are going to put both of them in the ice bath. Can you tell me why are you using ice bath? And Brianna, Victor, or Ahmed, any of you can answer that question. Why does it have to be an ice bath?
Solid.
Okay, in this case, both of them are in the liquid form. Step 1 and 2.
asking me which step?
Step 1 and 2, you are placing in the ice bath before you mix it.
Mm. Well, here's the thing. They're very exothermic, so you need to keep it low at a low temperature.
Mhm. So in step 3, it says that you add 1 drop. You add 1 drop at the time using the nitronium ion, the agent or the nitrating agent, into the metal benzoate, and you add 1 drop at the time. And you wait until the temperature gets back, cool down before you add the second drop. Can Michael, Karina, or Olavia, can you tell me why? Does it have to be 1 drop at the time, and you have to give time to cool down before you add the next drop? What would be a problem if you add too many drops of the acid, the nitrating agent, into the metal benzoate?
It will splash everywhere.
Is going to?
Everywhere.
You want to avoid any unwanted product, so you don't want it to become dinitrated. Is that correct?
Yes, one is the cause and the other one is the effect. The effect is going to be formation of a dinitro product, and the cause is that when you add the acid, like usually when you add acid to water, like it generates heat.
Right.
Yes. That's okay. You can type your answer, Natalia. So great. So it generates lots of heat. The reaction is the exothermic reaction, and since it generates lots of heat at the high temperature, the product is going to be either dinitro product, and that is a byproduct. It can decompose the nitric acid, and when it decomposes at high temperature, it gives lots of toxic gas of NO2, nitrogen dioxide, brown gas. Dinitro product also is a brown color. You want only one NO2 on the benzene ring, and then you, based on the melting point, you want to see if it's acid or meta, ortho, or para. You don't want 2 of them. So based on the experience or evidence, if the product is like a light yellow color, light tan color, is a nitro methyl benzoate, but if it's brown color, that means is a dinitro. So you want to avoid formation of a dinitro. That's why you're adding 1 drop at the time, and you wait in between drops. And you don't want that NO2 to be produced, because high temperature will cause NO2 to produce. Okay, next question. After you mix it all, then you leave it at 15 minutes, room temperature, then you put it on the ice, and precipitate will form. That's your product. And you're going to filter it, wash it with 10 milliliters of cold water. What's the purpose of washing with cold water? And that could be Melissa, Julia, Denise, if you can answer the question. What's the purpose of
it's an exothermic reaction, so we want to control the temperature.
This is after vacuum filtration, so the reaction is completely done. And we are on step 7. We wash it with 10 milliliters of cold water.
Oh, okay.
Ice cold water. Why is it important to wash it with ice cold water?
That was my answer from before, to precipitate the solid.
The solid is already precipitate, so when you're washing with cold water, you are trying to avoid redissolving of the precipitate. You don't want to dissolve the precipitate and lose the precipitate. So you want to keep the temperature of the water cold. With any recrystallization, when you're washing with the solvent, it has to be cold solvent, because if the solvent has high temperature, it would dissolve again. the solvent has formed, you filter it, vacuum filtration, but if the solvent is not cold enough, it's going to re-dissolve and you would lose the product. And what's the purpose of washing anyway? Someone said it in the chat. I just want to ask again. What's the, okay, to wash away any side product that they are soluble in water. So when you are using water to wash the product, you want to remove anything that is soluble in water. And then on the next step, it says to wash it with sodium bicarbonate. What's the purpose of washing with sodium bicarbonate? You want to first remove like the excess amount of the acid, because you have lots of acid, you're mixing nitric acid, sulfuric acid. You don't want to use the sodium hydroxide, the sodium bicarbonate first. You want to wash it with water. Sodium bicarbonate is not a drying agent. That was sodium sulfate or magnesium sulfate or calcium carbonate. This is a sodium bicarbonate. Is used to neutralize it. Okay, so you wash, you remove the excess of the acids first, and then you use the sodium bicarbonate to neutralize, to remove whatever of the acid that is left. And the next step, then you are going to wash it with cold water again. Why are you washing with cold water again? Gian, Therese, or Cindy? The cold part should, so the crystals do not melt. And what's the purpose of washing? Can we just stop after adding sodium bicarbonate? Or do we need to wash with water? To remove what? To remove any sodium bicarbonate that is left, right? Or any product that formed with the sodium bicarbonate. So anything that is, okay. Okay. After sodium bicarbonate, then you need to recrystallize it. After washing with water, you are recrystallizing with methanol. Can Christopher, Taylor, or Johns, can you tell me why do we recrystallize with methanol? What's the purpose of recrystallization with methanol? And I'm going to take it to the first page so you could see the reaction. You are going to recrystallize with methanol. What's the purpose? Side product, if you have a dinitro product, it will dissolve in methanol. What else? What else is removed? Beside the side product, what else is removed using methanol? Which impurities? Sodium bicarbonate was washed with water because it's water soluble. Recrystallization with the cold methanol, unreacted reagent. That means if there is any methyl benzoate that it didn't get nitrated, it would be removed with methanol. So methanol would remove any unreacted methyl benzoate. Also, it would remove if there was any byproduct. What I said earlier, if you have like a light tan color product, that is a nitromethyl benzoate. But if it's a brown color, that means you also have a mixture of dinitro. So when you recrystallize with methanol, that brown color would be removed, which is impurity of the byproduct. It would be removed. And unreacted reagents would be removed. On the next step after recrystallization, you are going to wash it with cold methanol. Of course, that's part of the recrystallization. And then you dry it at 65 degrees Celsius. Can I use 75 degrees Celsius for drying? Or can I use 55? Can I use 55 or 75? What's wrong with each one? What's wrong with 55?
Evaporate the solvent.
55 cannot evaporate the solvent. That's the problem, right?
5.
You want to use 65 to evaporate the solvent. The 75 is too high. It would melt the product. Okay, that's right. At 55 is too low, is not going to evaporate the solvent. So there is really no reason for you to use less than 65 because it's not going to evaporate the solvent. But you have to have an idea about the melting point of product. You don't want to set the oven close to melting point of product because you can't take out, it's going to melt inside the oven. So you want to make sure that's still a solid when you remove it by keeping the temperature controlled. And you are going to measure the mass. When you measure the mass and the melting point of the product, when you have the mass and melting point, that's basically you calculate the percent yield using the same formula that you had before. And this time you're using 0.4 milliliters of the methyl benzoate instead of what you had before. And you would need to use the melting point to identify your compound. Is it meta, ortho, or para? You also need the mass to calculate the percent yield. Percent yield and melting point should appear in abstract and as well as the conclusion, and also you would discuss using for discussions. Any questions?